Hey guys, what's up? I'm going to look at stationary waves and how we can use stationary waves to estimate the speed of sound. We're going to go through the method step by step, but let's start off by looking at what equipment we need. The first thing we need is a tuning fork. This is really important because tuning forks have a very specific frequency. They vibrate with a very specific note, which is a set frequency. We're going to use that because to estimate the speed of sound, we're going to use the wave equation. V is equal to F multiplied by lambda. The wave speed is equal to the frequency multiplied by the wavelength. So if we know the frequency, the only thing we need to measure is the wavelength of our stationary sound waves to determine the wave speed. We need a long column of water because we're going to raise a glass tube within it. And you'll see how we use this glass tube here. There's our glass tube and here's our water. And we're going to use those, we're going to move the tube within that water until we hear some stationary waves being formed. The last thing we need is a ruler because we're going to have to measure a distance to determine the wavelength of our sound waves. So let's get straight on into how we use this equipment to estimate the speed of sound. The first thing you need to do is place your glass tube, which is here, into the water here. And then you're going to place a vibrating tuning fork of known frequency above it. So you hit the tuning fork and you just place it above. And you shouldn't hear anything particularly straight away. You'll just hear the tuning fork vibrating very quietly or at a very specific note. The next step is to raise this glass tube up and out of the water until the fundamental note is heard. At a very specific length of this glass tube, we get a stationary wave set up. The reason for this is that the tuning fork sends out sound waves, progressive sound waves, which travel down this tube. When they hit the water, they reflect, and the incoming and reflected sound waves interfere and create a stationary wave pattern. But this can only happen at very specific frequencies and wavelengths, therefore very specific lengths of this glass column that is there. The water provides a closed end, so we always get a node here. And at the open end, we get an antinode where the air particles vibrate with maximum amplitude. So you'll hear this really clearly. It's important that you lift your glass tube slowly out of the water and then you adjust it until that note is as loud as you can possibly hear it. Because then you know you've got very specifically at the right point for the fundamental note to be heard. The next thing you need to do is get your ruler out. So here's your ruler and you're going to measure the length L of this glass tube. The reason why we're going to do that is because we've got this stationary wave set up, the fundamental note. We've got a node at the fixed end and an antinode at the open end. And you should know from your stationary waves knowledge that the distance from a node to an antinode is a quarter of a wavelength. Therefore, if you measure L, you know that L is equal to lambda over 4. Therefore, the wavelength of this stationary sound wave is 4 times the length of that glass tube. So if your tube was 25 centimeters, you know your wavelength will be 100 centimeters, 4 times L. We could just stop there and use the wave equation, but to be more accurate, we're going to repeat this process once more. We're going to lift our glass tube further out of the water until the note is heard again. So you can see we've got the stationary wave pattern set up here, and this time we're going to measure the length L2. And in this case, we've gone from a node to an antinode to a node to an antinode, which means that we've got 3/4 of a wavelength. So L is equal to 3/4 of a wavelength. Therefore, the wavelength is equal to 4/3 multiplied by L. We can now use this to take an average of the wavelength, and it just means that we're going to get some more reliable results. The last step is to simply use the wave equation. Use V is equal to F lambda. And we're going to use the average of our 2 calculated wavelengths so that we're being more accurate in our measurements and in our estimation of the wave speed. So just to recap it all, the method is you place a glass tube into water and you place your vibrating tuning fork of known frequency, really important, above it. Then you slowly raise your glass tube out of the water until the fundamental note is heard. Adjust it until you can hear it really nice and clear. You measure that length, L1, and L1 is equal to lambda over 4. Therefore, the wavelength is equal to 4L. You keep lifting the tube out until you hear the note again. And this time L2 is equal to 3/4 of the wavelength. Therefore, lambda is 4/3 L. Then you can average your wavelength and use the wave equation V equals F lambda to get a good estimate of the speed of sound in air. That's it. Thanks for listening. See you all soon.